So welcome everybody to our talk series. Today we have Ian Horrocks, and he will talk about knowledge representation and the semantic web, what we did right and wrong. So what is this? This is the talk series on knowledge graph research, which we started during the pandemic. And as questions kept coming in, when we will have the next talks, we think even without the pandemic, it's worthwhile to continue. So previously we had 3 sessions in 2021 and 2022. And today we have Ian Horrocks. The tradition of this talk series is that we source speakers from the people who received a Switzer Award from the Semantic Web Science Association. And among many other awards, Ian Horrocks won the 10-year award in 2013 for his work. We will have more talks to come in autumn 2023. So this year we have names, but we don't have dates yet, but we will announce them on our website, which you see here, the link. So there's more to come in autumn this year. What is this cost action? What is the cost action anyway? Cost action is a European research network which we have on the topic of distributed knowledge graphs. There are quite a few countries represented, and what do we do? Well, we run workshops, hackathons, and short-term scientific missions, especially those may be relevant to you. So you can, if it's a topic that's relevant to, if you're working on a topic that's relevant to the topic of the action, you can apply to travel for a short term to a partner across a European border and collaborate in research. This whole thing runs from September 2022 to 2024. It's chaired by myself and run by this number of people, which you see on the slide. So Axel Polleres, Remzi Celebi, Andreas Hart, Antoine Zimmermann, Olaf Hartig, Ed Curry, Anastasia Dimou, and Stefan Gostovic. Today, we have a talk by Ian Horrocks. He's a full professor in Oxford for computer science. He is member of many academies in Europe and the UK, and he's doing knowledge representation research. And that's why we are delighted to have him here to reflect on the semantic web. And before I hand over to Ian, I want to invite you to put your questions into the YouTube chat. The YouTube chat will be monitored, and after the talk by Ian, we will have a Q&A session. Yeah. Then we have an exciting hour or a bit more of talk and Q&A. And Ian, I'm looking forward to your thoughts about knowledge representation and the semantic web.
Okay, thanks. Thanks for the nice introduction. I'll try and share my screen. Hopefully that's going to work. Here we go. So hopefully you're seeing that now, yes? Okay, I'll take that as a yes. Good. Okay, so knowledge representation in the semantic web. What have I got to tell you about that? Well, I thought I'd just start out with a brief history of OWL, which probably isn't new to most of you, but this will all be rather personal perspective. That's the luxury I have in giving these kind of talks. So yeah, RDF standard came first. That was first published in 1999 and revised in 2004. And then this was extended with what back then was called RDFO. I think by now everyone just considers this to be part of RDF actually, but it extended RDF with some sort of basic ontology-like features, in particular sub and superclasses and sub and super properties, and range and domain of properties could be specified. But this was still pretty minimalistic as far as any kind of serious ontologizing endeavor was concerned, and it missed many features that we would like to have when describing non-trivial domains. And another issue that RDF initially had anyway was that at the beginning there was really no formal semantics at all. It was just a sort of, English language description of how things were expected to work. And actually, when we pushed into that, as we were beginning the work on defining an ontology language, it was pretty clear that there was no single agreed interpretation about actually what this kind of waffly description really meant from a formal point of view. And I remember discussions about range and domain in particular as to whether or not multiple range and domains should be a union or an intersection or what that could mean at all. Obviously, that was fixed later with a formal semantics for RDF. So, yes, back then another EU-funded project, which was the OntoKnowledge project, decided that it would really be a good idea to extend RDF and RDFS further to create a sort of fully fledged ontology language. And as part of the project, then we developed this language, which we called OIL. I think that stood for Ontology Interchange Language or something like that. Although I think there were many interpretations of the acronym to suit different purposes. And I think the sort of prime movers there were myself and Dieter Fensel and Frank van Harmelin. And here's some photographs of us all looking even more youthful than I did on the introductory photo that you saw a few minutes ago. So this was a while ago. At more or less the same time, the US DAML program, motivated by the very same sort of ideas, were developing this language that they called DAMLont. And it soon became pretty clear that as we were both, doing in parallel more or less the same thing, that we should really join our efforts, which eventually was agreed to do. And this thing called the Joint EU-US Committee on Agent Markup Languages, I think it was called in full, was set up. And the main people coming in from the DAML side were Peter Patel-Schneider, Pat Hayes, and Jim Hendler. And yet 3 more youthful photographs of those folks. Anyway, the 6 of us and a bunch of other people, I don't want to say there's just the 6 of us did everything, but those people and a bunch of others were joined together to specify this language, which became subsequently this DAML plus OIL language, which became the basis for the W3C standardization activity that eventually produced OWL. And the original OWL working group, which was actually called the WebOnt working group, because the name OWL hadn't even been coined then back in 2004, that actually came out of the working group. So that was called the WebOnt working group. And then in 2009, there was another working group set up to extend and refine the specification a bit to give OWL 2. Okay, so what about this OWL language? Well, actually, OWL is based on a logic, in particular a description logic. And, well, depending on whether we're talking about OWL or OWL 2, I think OWL was based on a description logic called, I've got a bit of a hybrid here because I've said Shoin, and I think the OWL language was actually based on a description logic called Shin, and OWL 2 based on Shoik, so the N should be a Q. These acronyms in description logics might look a bit scary, but really they just a list of the features of the language. So H means a role hierarchy, I means inverse properties, and stuff like that. Okay, so at first, people were a bit worried about these description logics, particularly with these funny acronyms and strange syntax. They seemed, obscure and exotic. But actually, if you really look into it, all they are is first-order logic fragments that, they have a clear semantics. That's just directly inherited from first-order logic, actually. They're just part of first-order logic, subset of first-order logic. And the goal with description logics is to try to find decidable fragments with good computational properties and to exploit that to develop effective goal-directed reasoning algorithms. And a lot of that work had already been done, and a whole bunch of these different description logics with different combinations of features, which correspond to kind of different fragments of first-order logic, had been explored, and reasoners developed for them, practical reasoners developed for them. So that seemed like a good basis for an ontology language. So yeah, following on from that, OWL is decidable, but the description logic Shoik, which is the basis of OWL2, and even the smaller one that was the basis of OWL, they're decidable fragments of first-order logic, but they're still highly intractable. So they typically have something like double non-deterministic exponential time, combined complexity, and they're even NP in data complexity. As I already mentioned, OWL2 was developed by this working group starting in 2009, and this was based on this slightly larger description logic, which I already mentioned. In addition to the slightly more expressive logical language, it also enhanced the aspect of the language which dealt with data types. So it had a much more detailed and expansive specification of the data types you could use in the ontology, and a bunch of other things. And another really important feature of OWL2, which I'll come back to quite a bit in this talk, is that it actually introduced some tractable profiles that are based on subsets of the main language that by the description logic community had already shown were actually tractable and had good, well-behaved algorithms for dealing with them. Okay, so I promised to say something about the whole OWL language design process. So I've got a sort of personal and rather maybe idiosyncratic review of the OWL language design and what I think we did right and what I think we did wrong. This isn't meant to be comprehensive. I just picked out a few what I think are kind of interesting features. So RDF blank nodes, actually several of the things I'm going to mention here are really already there in RDF and were just sort of inherited by OWL. And one of the things that OWL inherited was RDF blank nodes. And actually, the problem with RDF blank nodes, I think, was mainly due to the fact that when they were first introduced in RDF, they did, as I mentioned earlier, they didn't really have a very formal semantics. And so the intention behind them was not completely clear. But actually, I believe the intention was really just some sort of wild card that you could use when doing, subgraph matching and query answering and so on. Or if you wanted to create some sort of graph structure with some nodes in where you didn't really have a specific name in mind for them. But when the semantics of RDF was formalized, a whole bunch of, theoretical computer scientists came on board and decided that, oh, well, actually, probably the right semantics for that is existentially quantified variables. But then when more work was done on that, it proved that this resulted in RDF entailment, even for this kind of base layer of the whole language stack, which really is just capturing the data. This already had NP hard complexity for entailment, which, can't be good really. And it meant that the whole kind of stack thing is broken, at least with respect to the profiles. because we have this OWL layer on top of RDF, but OWL has profiles with polynomial and lower complexity sitting on top of an RDF layer, which already has NP complexity. So something's wrong there. The whole thing is broken. And as I say, I think the problem was that when the theoreticians formalized the semantics for RDF, they got kind of carried away and overdid it with blank nodes. Okay, so I mean, another thing about RDF that is restrictive is the fact that it only supports, well, actually really binary predicates, but in the case of the OWL type predicate, this is used as a kind of cipher for unary predicates. But not in any case, there's this limit to sort of at most binary predicates. And that can be problematical. And I mean, there are already sort of many efforts in train to extend RDF with this ability to deal with higher rarity predicates, and or to allow for things like having triples themselves as being the subject or the object of a predicate. So the downsides of this restriction is incompatibility with the databases, and you know that reification is often used in the data, and reification is introduces quite additional cost and sort of somehow makes the data be much less easy to understand. But on the plus side, often it's sufficient in practice, and it makes the whole business of graph data structures and algorithms much easier to understand and to deal with in practice. So I already mentioned the stack briefly. So one of the ideas behind OWL, and indeed its predecessors, Oil and Daml plus Oil, were to sort of have this, layering so that you got more and more kind of rich and complex languages in a kind of a stack, each of which was backwards compatible with the things underneath it. But again, that's nice in some ways, but it did lead, I think, some undesirable consequences. In particular, people wanted the RDF syntax of OWL to really somehow be semantically interpretable in RDF, which actually was a sort of futile endeavor. It's easy to prove that that's even, logically not possible. And it also led to this idea of OWL full, which allowed all of the kind of syntax structure of OWL in RDF to be interpreted in some way, even though some of the RDF triples that you could write really didn't seem to make much sense at all. The canonical example for that was an RDF triple of the form RDF type, RDF type, RDF type. So RDF type is subject, predicate, and object of that triple. What on earth does that even mean? It obviously doesn't really make much sense, but this OWL full language had to give a semantics to that. And there was a huge amount of effort spent on trying to do that, which to my mind was really a waste of time. Nobody actually uses OWL full. On the plus side, actually layering things in this way had quite a lot of advantages. We started with a simple and very effective and widely used graphical data model, which is RDF. If we view RDF just as the data model, which I think is the right way to look at it, it meant that we could exploit a sort of single storage and querying infrastructure. So our ontologies and RDF data sources all had the same syntax and could be processed by the same infrastructure. And you could even use the query mechanism to ask questions about the structure of the ontology as well as about the data, which can be quite useful. Okay, another feature that's kind of controversial, and actually I don't really want to say that this was right or wrong, was the open world semantics. So OWL inherited from its genesis in description logic and first order logic the open world semantics of those logics. Actually, I think this open world semantics is usually quite appropriate when you're designing the ontology, because you're making these kind of general statements about an only partially understood, many possible real incarnations of this ontology. And there were arguments that this was appropriate for the web because we could never really, know everything that was out there on the web. But on the negative side, open world semantics is not always very intuitive or appropriate, particularly if your main focus is querying large data sets, where people usually expect something more like a database closed world semantics. And it also makes it difficult to combine OWL with features such as defaults and negation as failure. And so finally, I guess one of the biggest arguments around the whole design of OWL was this, is it too powerful, too complicated? Lots of people said, I'm sure you've all heard the famous, a little semantics goes a long way, which can be interpreted to mean, I like to think of it as meaning semantics is really great, and even only a tiny bit is awesome. Think what you could do with a lot. But actually, I think it was meant to say that, it's all too complicated and maybe we need a little bit of semantics, but let's not get carried away. So there was this big tension anyway, even in the OWL working group, between people who wanted to make the language more expressive and people who said it was too complicated. And well, there are pros and cons, take your pick. And we can look at it either way around. So as I say, there were arguments in both directions. And similarly to this argument about whether it was too complicated or not complicated enough, there were also a bunch of people in the working group and outside the working group who felt that it missed certain features, or obviously the people who said it was too complicated said that it had, too many features that weren't necessary. So if you get, more than two people in a room, you can no doubt have a discussion, oblique argument about which features should have been in and are not in, and which features should have been excluded and are in. I'd like to sort of finish the discussion about what was good and what was bad by, really just sort of reiterating this point that no two people are ever going to agree what was exactly the right language. And I think in the end, the reason we sort of succeeded was that we all came to the conclusion that actually agreeing on some standard was, regardless of what it was better than having no standard, and that having a standard would be the only way to really kind of move forward with the whole semantic web, semantic technology endeavor. And I think that we can, hopefully with hindsight, we can all see the benefit of that, and that having this set of standards, RDF plus OWL plus SPARQL, has been, a massive success. I bump into people all the time just out there in the wild, in industry, who know these standards, that use them and are very happy with them. And it's had an enormous number of benefits, I think. Okay, so I'm just going to move on a bit now from this, what should have been in and what shouldn't have been in. We've got the language, let's just deal with it and, see what we can do with that. One of the things I think actually turned out to be really important and beneficial with OWL, it was the foundations in academic research. So as I already mentioned, it had this formal and precise logic-based semantics, and this meant that we already had formally proven algorithms that could be the basis for sound and complete and empirically effective reasoning systems, notwithstanding the very high worst case complexity of the language. Moreover, in OWL 2 anyway, we actually introduced these tractable profiles, which again came from foundational academic research where people looked at these expressive description logics and identified subsets of features that would result in tractable languages, and also developed new kinds of reasoning algorithms that were very effective for those tractable profiles. And I think this was really important, and you can contrast that with the development of OWL Lite in the original OWL working group, which was really a bit of an afterthought and actually just came from sort of cherry picking a subset of the features without any real consideration of the computational consequences of that. And actually it proved subsequently that, it was easy to show that OWL Lite was still highly intractable, didn't really offer any computational advantages with respect to the whole language. And well, I don't think anybody even remembers OWL Lite anymore. So another big advantage that we got from, working using academic research as a basis was that people were also developing a huge range of really interesting and useful tools for doing all kinds of different tasks like integration, visualization, debugging, axiomatization. There's a long list, and these are really useful in practice. And again, a part of the reason I think why this kind of language stack has been effective and is used in practice. And you can see actually that this kind of formal basis also leads to a high degree of interoperability. There are a whole bunch of different OWL reasoners out there, and people can really switch between them and be confident that they'll get the same results. And in fact, if you really try this out at home, you'll discover that, the degree of compatibility between different OWL tools and systems is really impressive. Again, I think this comes from this academic research background. I just wanted to say something very quickly about this argument actually between undecidability and high complexity, which was going forward quite a lot during both the working groups, but mainly during the original OWL working group. So there were some people in the camp of, it's not expressive enough, who felt that OWL should have been based on at least full first order logic and perhaps even common logic, which sort of extends first order logic into with some sort of higher order flavor. And they sort of argued that, well, once we have this very high complexity, we know that in some cases the reasoner will choke. And so, well, what's really the difference between that and undecidability? And they also kind of made this analogy to the web and said that, it's just like you'll have some 404 errors. I'm not able to do this reasoning for you. But I'd argue that this just doesn't really chime with what we find in practice, which is that in practice, even state-of-the-art first-order logic theorem provers are far away from being like the sort of turnkey systems that we're used to with OWL, where we just press the button and, 99 times out of 100, it terminates in a reasonable time with all the, entailments that we needed to compute. In contrast, first-order logic provers are very bad at proving non-subsumption, for example. And so the analogy would really be that almost every link ended in a 404 error. And I think if that was the case, people would soon get very sick of, browsing around the web. Okay, and another thing that I just wanted to mention actually about this was another argument that was around a lot and is still probably, you still probably find a lot, is that, well, we don't really need to worry about this high complexity because, well, we'll just build incomplete reasoners. But actually, I would argue that incomplete reasoners in general are quite bad, because actually what incomplete reasoners typically do is they don't report either, yes, this entailment holds, no, it doesn't hold, or third case, I wasn't really able to figure it out. Usually this third case, they just interpret as no. So either they'll always give you a yes or no answer, even if in reality they weren't able to figure it out. And no, this isn't the same as negations failure, because in negations failure, we have a clear semantics. We actually know that the ontology doesn't entail whatever the concept or formula or thing it is that we're interested in. And if that's the case, then we conclude that this thing is not true. That's the semantics of negation as failure in general. But with incompleteness, actually, we just don't know whether this thing follows or is entailed or it isn't entailed. And the other thing about incompleteness is actually it can easily become unsoundness in downstream applications. Imagine this scenario where we have an allergy app running on our phone. We have some, food allergy. We want to make sure we're not eating anything that's going to be harmful for us, even very dangerous for us. And our app is equipped with a very comprehensive ontology of foods, and it tells us that the food is safe. Food F is safe if it doesn't contain allergen A, for example. But if we have an incomplete reasoner and we use that to check, does our ontology entail that this food F contains A, it might just fail to find that subsumption and conclude that the subsumption doesn't hold. That's incompleteness. But then it tells us that F is safe to eat because it didn't find this entailment. Obviously, that's very dangerous, and that is sort of unsoundness in the downstream application. So treating don't know as no is just wrong. Don't do it. I said I was going to come back to the profiles. I'm just going to quickly mention something about them. So OWL2 introduced 3 profiles based on these 3 description logic fragments: EL++, which has p-time, worst case complexity for both combined and data complexity; OWL2QL, which is based on the DL Lite description logic. And this has actually this AC0 data complexity, which is a complexity class that's inside log space and is the same complexity as relational databases. And RL, which is based on somehow the intersection between description logics and logic programming, and also has p-time data complexity, combined and data complexity. So for schema reasoning, which is where we're mostly interested in reasoning about the ontology itself rather than about data answering, we've got 2 options there really with OWL2. We can either use the full language, and by the full language, this is one of the reasons I really dislike OWL full, because it's very confusing when we talk about the full OWL language. When I say that, I mean, without any kind of fragment restriction. So with the full OWL language meant in that sense, we have a bunch of reasoners that are available. They typically use this hypertableau model construction approach. But there's a high worst case complexity, as I already mentioned, but they're actually surprisingly effective in practice and are quite widely used. If we have really stringent requirements about the time taken for the computation, or we want to work with really, really large ontologies for which some of these above mentioned reasoners may be not so effective, then we can switch to the OWL2EL profile. This imposes some constraints on what we can express, but the reasoners there have this p-time worst case complexity. They use a different kind of consequence-based deduction theorem proving technique, which is super effective in practice. And, typically they can completely classify even monster ontologies like SNOMED in just a few seconds. So we might even say that ontology schema reasoning is kind of a solved problem if we look at a bunch of different ontologies with different expressiveness. if they're inside this EL profile, which is the top half of this picture, then the Elk reasoner, for example, can deal with everything, even up to this large SNOMED ontology I mentioned, in seconds. And these results come from a long time ago with old computation hardware. So the modern results are even much faster than this. And for more expressive ontologies, there are a whole bunch of different reasoners. The interesting thing about that is that for every ontology, we can always find a reasoner that can deal with it, but it's not always the same reasoner, and different reasoners behave in different ways on different ontologies. And this is actually what you get with these high complexity classes. Not that you can't do anything, just that the systems tend to be much more temperamental and subject to big swings in performance depending on just exactly what's there in the given input. So I wanted to just switch over and talk a little bit. I've got a few applications here. Actually, I just want to make the case for success of OWL as an endeavor and the kind of infrastructure that we as researchers in the semantic web community have developed. The result of that is that it's actually OWL's pretty widely used out there. I'd say for this ontology-centric mode, it's a little bit more niche. It tends to be healthcare and life science applications, but there are also applications in industry. For example, this third one I mentioned here, where they use an OWL ontology to basically develop a large structured catalog of components that they use in building complex physical infrastructure, such as oil platforms and the like. So I would say it's been pretty successful and it's quite widely used. But probably there are many more applications that are really interested in querying data with an ontology in the mix, rather than necessarily just focusing on the design of the ontology itself. And actually, this is quite problematical for the full OWL language based on this Schema description logic. In fact, the decidability of conjunctive query answering for that language is still an open problem. So if any of you out there are, more theoretically inclined and interested in working on that, it's still to be shown one way or the other. But it only takes a very minor tweak to the very minor restriction on the form of the query or the ontology before we know it is decidable. But even if we apply those constraints, then it's really hard to see how these reasoning systems can scale for that, can scale to big data sets, because basically they require an entailment test for each candidate answer tuple. So if you have a query with, an n tuple answer, then basically you have to construct every possible n tuple from the data and ask the question, is that tuple entailed by, entailed as an answer to the query by the ontology? And this just isn't going to scale to large data sets. The QL and RL profiles were introduced exactly for the purpose of dealing with this issue and providing subsets of the language for which we could provide scalable query answering services. So how did they work? Well, this QL profile is designed such that you can build reasoners that use a technique called query rewriting. And the way query rewriting works in one sentence is that it uses the ontology axioms to rewrite the query by treating them as sort of backward chaining rules. And note that this process is independent of the data. So we rewrite the query such that the expanded query will give us the right answer regardless of what the data is. And here's a very trivial example of how that would work. If we had a query that just wanted to return all instances of the class D, and our ontology tells us that C is a subclass of D, then if you think about it, if we use this kind of backward chaining, well, if we're interested in Ds and we know that all Cs are Ds, then we actually also have to be interested in C. So then we use that to rewrite the query, and we end up with this union query that says, give me all of the Ds and all of the Cs. And that query, that's the totality of my ontology. This query will give me the right answer, regardless of whatever the data set is. And we can use that query directly, actually, if our data is already in RDF. But another nice feature about query rewriting is that we can leave the data in relational databases, and we can just define with some mappings how we retrieve the various RDF predicates and classes from the database using this mapping. So we can just translate our query into SQL and answer it directly over a legacy data source. So the good thing is that this gives us this log space AC0 complexity, sound and complete answers, providing I'm inside the profile and I can leave the data in legacy data stores. The downside is, to make that work, the ontology language has to be really minimal. It doesn't even support conjunction on the left-hand side of these inclusion axioms. The rewriting process itself can be quite slow. If you have a big ontology, applying this backward chaining process can really blow up the size of the query, which can take some time. And the resulting query could then be actually quite hard for database systems that typically aren't optimized to answer these kind of huge rewritten queries. But there are a bunch of systems for that who have various optimizations to deal with some of these issues, and can work quite well in practice, depending just, what the application looks like. So the other choice you have, if you're mainly interested in query answering, is to use this RL profile. And reasons for that are mainly based on a technique called materialization. And this just does sort of the opposite thing. It uses the ontology to expand the data by treating the axioms as forward chaining rules. And in contrast to query rewriting, obviously this isn't independent of the data, but it's independent of the query. So we don't need to know about the query at the time that we're doing this materialization. And taking the same example, the way that would go is, if I have my ontology that says C is a subclass of D, and I have some data that says A is an instance of C and B is an instance of D, then if I treat this axiom as a forward chaining rule, it says, every C is a D. I know that A is a C, so I have to conclude that A is also a D. I add that to my data. Actually, in this very simple case, I'm done. And now I can just go ahead and answer whatever query I want over this expanded database, and that will give me the right answers. And so that's how that works in materialization. So this is p time in the size of the data, which obviously isn't as nice as log space, but it's still tractable in the sort of formal sense. And this rewriting process is guaranteed to give me sound and complete answers. And another nice feature is that materialization is a pre-processing step. So I do that once, and the cost of that could be quite high, but it's sort of amortized over my queries. So if I'm going to answer a bunch of queries, I can answer all of them really fast. And this sort of pre-processing cost, doesn't look so bad. Yeah, the bad side is I still need to restrict the expressivity, but not nearly as much as for QL. Materialization could be slow and could increase the size of the data. And there's this issue of what happens if I change the data. In many systems, that means just going back and redoing the whole materialization process, which, as we've already agreed, could be quite costly. And this is a pretty popular technique, though, and there are a bunch of available systems out there. So I can see time's running on, so I'm going to just skip a bit through some slides. What I just wanted to show in these next slides is that actually having one of these RL reasoners you can do a bunch of pretty nice things with that. You can actually do EL query answering with that via a combined technique. I don't have time to go into the details. You can find that in papers or look at the slides afterwards. I can also use the same approach for QL reasoning. I can do ontology reasoning actually by a little trick that isn't too hard to see how that works, but I don't have time to tell you about it now. And I can even do reasoning for the full OWL language by using this kind of lower and upper bound technique. So if actually I just throw away all the non-RL, throw away all the non-RL axioms from my ontology, and I do a query answer over that, that gives me a lower bound. So all those answers are good answers, but I may have missed some answers. I'm obviously incomplete. But actually, I can use some clever tricks to transform those axioms into RL axioms in such a way that I actually strengthen the ontology. So skolemizing existentials is one of the things I do. And if I answer the query again using that ontology, I actually get an upper bound answer. And, then I have this lower and upper bound. I've got the lower bound I know is sound. The upper bound is complete, but maybe unsound. And the difference between the two tells me, if there are any tuples that might be in the answer. And if I care about that, I can go off and do some more processing, perhaps using a reasoner for the full language. So that the fact that RL is pretty cool and I can do a lot of things with it motivated us to develop this system called RDFo, which is a materialization-based reasoner. So it has a lot of good features, as I've just been saying. The challenges are that materialization can be costly in time and memory. I might need to repeat it if the data changes, and the expressive power of the ontology language is still a bit restricted. So we developed RDFox with a view to try to address some of those features. In particular, we developed this parallelized materialization process with an optimized in-memory data structure that tries to make the materialization process be as fast and effective as possible. And we did a lot of work on incremental maintenance of the materialization. So RDFox actually allows you to not only change the data, but even to change the ontology, and it updates the materialization rather than redoing it from scratch. And I just wanted to hark back to foundations in academic research where all of this stuff is backed up. The correctness of all of this stuff is backed up by, a great deal of academic research and papers that you can look at and check that you really believe what we're telling you. And well, if you look at other systems that were built in a more ad hoc way, they're often quite broken, but I don't have time to go into that because I better finish up pretty soon, so you can ask me some questions. The last thing I wanted to mention was language extensions. So once you limit yourself to RL, actually you can ease up on a few of the other restrictions that OWL imposes. For example, you can really deal with arbitrary rules, not just the tree-shaped rules that you get from RL. You can do a lot more with data types and values, so have built-in functions and aggregation and all those cool things that you need in realistic applications. And you can also extend the language with constraints and negation as failure so that you can deal with shackle and even a lot more than shackle provides. So having done all that lot as academic research, this sort of motivated us to actually try to deploy it in practice. And for that, we had to sort of commercialize it in a spin-off company. The only thing I'm really going to tell you about that whole process is that it turns out that there's a hell of a lot more to moving an academic prototype into a company that you can actually, a tool that you can actually sell to big companies than you might think. And we had to spend several years actually building a whole load of additional infrastructure around that. But the core algorithms and reason are still, are based in academic research and are still kind of correct. Yeah, and it was quite successful. So we have a bunch of applications for that, which I don't have time to tell you about. But, you know, big companies are actually using semantic technology, and not just RDFox, but there are several other companies selling, you know, RDF store systems that are used by, you know, big companies. It's a mainstream application now. So I finally, sorry for rushing a bit through the last part, but I finally got to the end more or less. So the discussion, impressive progress we made on schema reasoning. There are still issues. EL reasoners are still the only reliable solution if the ontology is super large. And impressive progress on query answering as well. So with RL systems, we can now deal with really large data sets. We can provide fast and effective reasoning. Of course, there are always issues remaining. As researchers, I suppose we should be happy about that because it gives us some motivation and ideas to go off and work on new things. So RL may not be expressive enough for all applications, and materialization perhaps imposes some limit on the dataset size, even if we can handle pretty large data sets. So I'll stop there. Sorry if I overran slightly, but yeah, I was so excited to tell you about all of that stuff. As usual, I put too much in the talk. Sorry about that. I'm ready to answer questions.
Thanks a lot, Ian. So we will take questions in the chat, the YouTube chat. Feel free to write your questions. We have a slight delay of a few seconds, so I might see the questions a little bit later. Therefore, maybe I can start with one question that I had.
Yeah, or let's introduce the moderator for the Q&A first. So we have Olaf Hartig, who gave the previous talk in our talk series, and he will moderate the Q&A, and obviously then he also has received a Swither award. Until we wait for the questions, maybe a short round of virtual applause for the speaker, and we hope for questions to come in.
Perfect. Okay, so one of my questions is, at some point in the talk, kind of in the somewhat more in the beginning, you mentioned that RDF can be viewed just as a data model. And you said this is kind of, from your perspective, the right way to look at it. Can I interpret this statement that you would say that actually it should not be necessary, or we shouldn't define a semantics for RDF itself, but instead semantics should be defined for languages on top of RDF?
No, I didn't mean that there should be no semantics, but that the semantics should be really simple and trivial. You know, so basically, the function that most people use RDF for is just to describe their data. You know, it's the contents of their database. And the semantics of that, as I say, is kind of trivial. So, you know, a triple could just be viewed. Well, obviously, we have this little trick in RDF where we use RDF type to sort of simulate unary predicates in first order logic, and then other properties are just binary predicates, right? And the semantics of that is just unary and binary ground facts, the end. And there's a little bit of extra work we have to do because of blank nodes, but I think if we treat them as sort of scolums in some way, then that's about it. So it still needs to have a semantics. So, you know, but it should be that simple. I think this base layer should be that simple. It's just the data, more or less the same as, you know, relational databases. End of story. And then we can layer things on top of that, so that the sort of thin layer on top would be just, you know, classes and subclass and subproperty and so on, and we can sort of build it up from there, and the stack really works. But if we bung too much stuff in on this bottom layer, you know, we're already in NP hard territory before we even put anything on the top, which is, you know, crazy.
I see. Yes. Anton Zimmerman asks, Wikidata is a huge success that is mostly based on semantic web technology, but it doesn't use any ontology language per se. Should this be considered a bug or feature? And is it a good thing or a bad thing, and why?
Yeah, that's a really good question. I mean, obviously, Wikidata does have an ontology, and it does have all of these kind of ontology-like properties. It chose explicitly not to reuse the sort of RDF and OWL ones, as I understand it. And I can sort of see the reason behind that, because it means that Wikidata itself is sort of independent of any specific language. And of course, you can easily find all these Wikidata properties and map them to RDF properties if you want to. So you can kind of treat it as RDF and subclass and RDF type and so on, if you want to. If you don't want to, you can just, take it as a kind of knowledge graph with no real semantics for the edges, other than the language, whatever the language label says that it is. And I think probably for uptake, that was a wise choice, because people can do with it whatever they like without feeling that they're really abusing it.
Mm-hmm. Sounds good. One more question that Tobias asks. In your talk, you talked quite a bit about theoretical computer science in the different places, like for blank notes, for query processing, and so on. The question is there useful theory and less useful theory? And how can you tell? Would you be able to tell only in hindsight?
Yeah, I mean, that's a really good question. I think actually the simple answer is yes. You can only tell in hindsight. I mean, I think as computer scientists, regardless of where we view ourselves as being on this theory to, practical spectrum, which, by the way, is pretty much endless in either direction. I mean, I've loads of times in my career, I've been in rooms where people consider me to be the theory guy. And loads of other times I've been the grubby practical guy, I mean, it just depends who you're with on the day. And whatever we're doing as academics, we never really know how that's going to work out down the line, how useful it's going to be. To some extent, that's inevitable. If we knew that already, it wouldn't really be research. So, yeah, I think that's true of theory. I mean, I do think there is a bit of a danger when you're trying to do things like language specifications and whatnot, that when computer scientists come in and, theoretical computer scientists, wherever we think they live on this spectrum, whoever we think theoreticians are, they can get a bit carried away, for them, things being complicated can be quite nice, because it's a hard problem and I can write a lot of papers about that, and, solving that's going to be really difficult, which is, that's a good thing. But obviously for a lot of us, even in academic research, we want things to be a little bit simpler. So that was all I was trying to say.
Okay. Now there are a few more questions in the chat. I picked this one here first. Can you comment on the rule interchange format RIF versus SWIL for rules? Is this something that you...
Yeah, actually, this is an issue that's really come up in sort of practice for me, and with my kind of, spin out hat on, because, our RDFox reasoner, obviously, it can take OWL-RL ontologies, but it can also just take arbitrary rules. And it would be really nice to have a kind of rule language standard out there that everybody was using, so that, we could just say, write your rules in whatever the standard is and we'll deal with that. But actually, more or less every system out there that uses rules has its own kind of syntax. And there is this RIF standard for rule syntax. But unfortunately, I think the problem there was that at the beginning, there were many people with a different view of what rules were, because actually rules are so kind of universal in computer science. We can describe almost every algorithm as just a bunch of rules in a certain way. So there were all these people with different ideas about what rules were. So they came up with this incredibly complicated specification that was like all things to all men, from a sort of rule perspective. And it was so complicated that nobody uses it in the end. And that was really a pity, actually, of a sort of standard just for basic, RDF style rules would be really useful. Swirl, it was never really intended to be any sort of a standard. It was just actually showing, layering some rules on top of OWL, thinking of the predicates in the rules just as being OWL concepts and whatnot. That's not rocket science. And actually, it amazes me that this kind of paper we wrote on Swirl ended up being maybe my most highly cited paper. I mean, this is typical again for research, isn't it? Who knows how that works out? Because it was something we did on the back of a napkin when we were, having dinner at a conference sometime. It's not rocket science.
Okay. Cool. Another question, Christoph Ray asks, what do you think of integration of OWL with logic programming languages? Is this an alternative to query answering solution?
Yeah, I mean, actually, I think maybe what you mean is to ask, can we use logic programming systems as a way of kind of computing query answers, I'm guessing, because actually, I mean, our LRL, as I said in the talk, basically is just defined as the intersection between logic programming and description logics. So from that point of view, the language already is a logic programming language when you view it from that side. The question of how you then actually answer the queries, yeah, absolutely sure, you can use logic programming systems. And I think some of the, LRL systems are in fact based on logic programming engines. So yeah, totally, why not?
Okay. Good. So now we have a question about another ontology language, namely F-logic. What are your thoughts about this? Jürgen Angele asks this question.
Yeah, I mean, F-logic was another take on ontology languages back in the day. That I think this F stands for frame, actually. So it was more oriented towards providing a formalized semantics for frame systems. I just refer back to my slide where I said, the most important thing actually was just to agree something. It could have been F-logic. Maybe that would have been okay, actually. I even forget the details of F-logic. I mean, it was so long ago. I don't think a lot of people are really using that these days. I haven't bumped into it in a while anyway. I don't mean to deprecate it. Just seems that it didn't really, win out in the popularity stakes. That doesn't mean to say it was bad or a wrong design or something. It's the sort of, usual thing that the main thing is to have a standard.
That makes sense. Okay, Josh Shinavir asks, are you aware of any work that combines OWL with intuitionistic logic?
I'm going to say yes, as I'm not sure off the top of my head I can actually give you a reference to a specific paper, but I think OWL, people have tried combining it with all kinds of other different logics, and it's just a fragment of first order logic. So yes, why not?
Okay, let's take one last. Axel Poleres comes back to Wikidata and collaborative knowledge graphs in the semantic web, for instance, also semantic media wiki instances and so on. And he says that that we see either very modular or very shallow schemata in these knowledge graphs. And so the question then is, how are axiomatic schema languages, are they still useful here?
I think they're still useful, actually. I mean, even if you only do things in a relatively simple way. So I used to know I'm not so much familiar with what goes on in Wikidata, but I used to know quite a few people who worked on the Google Knowledge Graph, although I think most of them have moved on to other parts of Google now, but they weren't necessarily, using some semantic web technology directly, but they exploit a lot of the same ideas about having a schema that they can use to sort of automatically expand the knowledge graph with things that would be entailed by relatively simple axioms. I mean, one of the things I used to have a talk where, I gave this example of, things that were located in the UK. And then you have, axioms like, London is in the UK and anything that's in London is in the UK. And all of those kinds of things, which Google exploits so as to be able to, answer queries like, is Buckingham Palace in the UK? Well, if you didn't have those kinds of schema axioms, you'd need for every single thing in the UK, you need to specify which city it's in, which street it's in, which town it's in, which city it's in, which county it's in, which country it's in, which, continent it's in. Is Buckingham Palace in Europe? So, I mean, actually doing all that manually would be an incredible amount of work. So just having some basic axioms that capture some of those things and automatically enriching the knowledge graph that way, which is just materialization, the way I described it. Without that, actually, I think you'd be dead in the water trying to maintain any kind of large scale knowledge graph.
Sounds good. Makes sense. Okay, I think we can close the session. We are already a bit over time now. Thanks a lot, Ian, for this very nice presentation, also for the answers to the questions. Again, everyone who's watching, we will have more speakers after the summer. 2 more are already lined up, and we will announce them very soon. Thank you, everyone.
Thanks, guys. Bye.